Hello and welcome everyone to this webcast on the occurrence of microplastics in water. Size does matter. We have over 970 participants and quite a number of folks from around the world, including Australia, Europe, Tehran, Puerto Rico, Latin America, a few friends from Colombia. Welcome. So before we get started, I'd like to take a moment to introduce and reintroduce the Water Research Foundation, which was launched January 1st, 2018. The Water Research Foundation is a nonprofit and educational organization that funds, manages, and publishes research on the technology, operation, and management of drinking water, wastewater reuse, and stormwater collection, treatment, and supply systems, all in the pursuit of ensuring water quality and improving water services to the public. The new foundation has approximately 1,200 subscribers, 2,300 research studies, and a 700 million portfolio. For the water quality community, the integration offers a stronger, broader, more interconnected research agenda with greater value and services to subscribers and funders. We're stronger together. The integrated organization also provides the water community with access to an expanded collection of water research, leverages funding more successfully, shares a greater knowledge base, and more effectively communicates new results and research needs with state and federal regulators. So before we get into our presenters, I have a few housekeeping items. You can submit your questions through the question box at any time. I also have an assignment for everyone, which is what is your top priority research question on this topic of microplastics that you would want the Research Foundation and other key water stakeholders to pursue? And when I say key stakeholders, I mean NOAA, USGS, EPA, international government entities, and just please caption it for me by saying top research priority so that that could be taken. There will be a live poll after the first presenter, and I expect everyone to participate in that. And then we'll do our Q&A near the end of the webcast. And during the Q&A, please indicate to your best of ability which one of our experts you would like to address your questions. Finally, please be sure to take the survey at the end of the webcast. The slides and recording will be available on our website within 24 hours. Okay, so just a quick run through of the agenda. We have 4 speakers today. Dr. Alan Burton will have a live poll, and then Per Henrik Nielsen for VCS Denmark with a case study featuring a biological nutrient removal facility. Shelley Walter from Sanitation Districts of Los Angeles County to give us some microplastic in water, wastewater, and the policy implication. And then our final speaker, Dr. Belinda Strom, to speak about a collaborative research with the Foundation and NSF on the fate and removal mechanisms. And then I'll just lastly, real quickly, give you some ideas of some activities and resources that the Foundation has, and we're certainly looking for more. So with that, I would like to introduce our first speaker, Dr. Alan Burton, who's been with us from the very beginning of just talking about this topic. And Dr. Alan Burton is a professor at the School for Environment and Sustainability at the University of Michigan. So without further ado, because we have a full hour and a half, I would like to turn the mic to Dr. Alan Burton.
Okay, thank you, Lola, and thank everyone for attending. It's really a fascinating topic that's changing quickly. I'm going to try to put things in perspective today and raise some points that I hope you find interesting and and maybe talk about perspectives and things we should do in the future. First off, just a reminder to everyone that in human-dominated watersheds, we're dealing with a wide variety of stressors that many of these we already know quite a bit about. We are dramatically altering the habitat environment. We typically have nutrient issues, pathogens, pesticides, even in our urban environments, we have lots of pesticides that are entering our waterways. The primary petroleum products coming in the urban environment are the polycyclic aromatic hydrocarbons, the PAHs. We've become more aware in recent years that we are also discharging a lot of pharmaceuticals and personal care products. We've always had an issue with a lot of metals because they're a natural product. And then in our northern environments, or colder environments, I should say, we have salts that are being applied a lot during the winter time. Just an aesthetic litter problem. And tire particles that you don't hear about much, but you know, there's billions of tons of tire particles that are entering our waterways, and we don't really address that. These tire particles are made up of a number of organic chemicals and a few metals such as zinc, and we just don't know much about that. And then today's topic, of course, of microplastics. And here's a picture that kind of shows you a size distribution, since we're talking about size, of a typical manta trawl. And the manta trawl is an instrument that the biologists developed decades ago to sample phytoplankton or algae in water. And so it scoops along at the surface of the water and captures particles that range in size, but typically the lower end of a manta net is down around the 300 micron or 0.3 millimeter size range. So here you see that we have a lot of larger particles that are being captured, but the ones that we typically are calling the microplastics are in that last vial on the right, the 0.5 to 0.3 range. You're very aware of the pictures you've seen so much in the news, and here on the right we've got some pictures of macroplastics that fish-eating birds or fish that scoop up birds that either scoop up fish or the eggs that float on the surface. You see how many plastics they accidentally intake. And then we have a fish here that has ingested a number of macroplastics. And then, at the microplastic level, you can see the daphnium, which is a very common zooplankton that we use for toxicity testing because it's very sensitive. And some fluorescent particles there on the right, you see the daphnia that's a filter feeder has pulled in these microplastics, so they can accumulate inside of an organism. But let's talk about whether that's really an issue or not. The next slide is showing the reality is that the plastics are not going away. Their production is going to continue to increase despite efforts for it not to. The primary macroplastics that are out there, the ones we've heard about in the Pacific Gyre, that's the size of the state of Texas, are debris like bottles, packaging, bags, but the dominant macroplastic that's out there is actually fishing nets and fishing lines. Those things are really not going to go away, and they're going to continue to be a problem. And here you can see some kind of the history of plastics and some of the figures on predictions of production. So this is going to be a topic that we're going to be talking about, I think, for a long, long time. One of the issues that's been in the literature a lot in the last 5 years or so is the concern that pollutants that really are toxic or that can bioaccumulate are adsorbed onto the surface of microplastics, and that certainly does occur. And here you see some data that was published back in 2009 and 2011, showing concentrations of PCBs that were adsorbed to plastic pellets that were recovered from sandy beaches in various parts of the world. And you can see some concentrations there that are high and that one would assume might be a problem, because if they were ingested, that means those various contaminants that are not only the nonpolar organics and the pesticides, but some of the metals would be consumed and potentially cause adverse effects in the organisms. The next slide is focused on the Great Lakes, where I've done some work, and there's been a fair amount of research done in the last 5 or 6 years, and you see concentrations that were recovered there in the left graph on some transect trawls that were done across Lake Superior and Lake Huron and then through Lake Erie. Lake Erie is the smallest, the shallowest lake, and the one that's got the most city, urban areas around it, and not surprisingly, it's the one that has the largest concentrations of microplastics. And here you see some pictures from Erickson and some others that did these surveys. And then look up there on the right, you see some of the figures there. The average abundance that was being recovered of microplastics was about 43,000 particles per square kilometer. The worst that was found in Lake Erie, they've gone up between about 500,000 and 1 million particles per square kilometer. Most of these were that were recovered there in Lake Erie were pellets. Some were coal particles, coal fly ash, and probably coming from non-point sources and from wastewater treatment plants. So the question is, I mean, those numbers sound pretty awful. Are they causing a problem or not? I'm the editor-in-chief for this journal, Environmental Toxicology and Chemistry, which has been around for about 35 years. And I look at about 1,000 abstracts a year, and I've been keeping on top of this microplastic literature for the last few years. And we're averaging over 150 peer-reviewed scientific publications per year in the good quality journals, and that is a lot. But I want to remind you all, I guess a lot of you probably already know this, but the peer review process is not a stamp of complete validation. The peer review process is only as good as the people doing the review. And anytime you have a relatively new topic, it's hard to get scientists who I guess are doing research in that area or have know some of the issues. And when it comes to ecological risk and the fact that this is such a popular topic, a lot of these papers are being reviewed by people who have relatively little ecological risk experience, and they are addressing risk issues such as adverse effects. So that raises a red flag, and whenever that happens, that means you have to look into the methods, the scientific methods that were used, to make sure that everything's legit. So let's start talking about that. I've got listed here the various methods that are used for quantifying the number of particles and the types of particles that are out there. And you see some pretty strange names of some pretty advanced analytical equipment listed there until we get down to the last one, optical microscopy. And believe it or not, that's the way most of the microplastic work that's being reported is being evaluated and quantified. And there's been a couple of different studies that have actually looked in depth at some of these studies, and you see there in bullet number 3 a pretty alarming number that 30 to 70% of the values being reported are false positives. Now, why would that be? How would it be that people are mistakenly identifying a particle as a microplastic when it's not? Well, all you have to do is take some water that has no microplastics in it, maybe from your backyard little pond you may have, and look in it, and you'll see lots of particles. You'll see lots of little particles. And these particles get enumerated as microplastics many times. So we see an overinflation of some of the numbers that are out there for just ambient surveys. Now, that doesn't bother me too much, and you'll see why in a minute as we get to the punchline. The standing rule now is if you really want to do a good job of quantifying microplastics, you probably should use 2 different types of methods because they measure different things. And the plastics vary so widely in what they are made of that some analytical approaches measure different conditions or characteristics better than others do. So these top 2, the Raman microspectroscopy and FTIR, are regarded as the best for not only quantifying but telling you the types of particles that are there. Why would you want to know the type of particle, type of plastic? Well, that helps you then trace back to sources. Where are these things coming from? And if you know the kind of plastic, you can do that. Now, let's get to some of the issues, and I'll come back to this statement there at the bottom about fibers and fragments. Here's some pictures of some of the headlines that have come out in the last few years, and this is just a sample, but I'm just trying to make the point here that the public knows well about the issue, and the topic of microplastics is being very much mixed up and integrated with the macroplastics, which have the horrible pictures that you've seen of the sea turtles and being strangled, and all kinds of wretched pictures that I see almost every week in the news. And one thing that kind of got me going originally was when I saw that top right one there, that the state of New York was banning microbeads. I don't know why it keeps jumping around like that. I'm not touching it. But the state attorney general of New York said that we are going to improve the waters, greatly improve the waters of New York because we're banning microbeads. And that's when my red flags went up, and I started questioning a lot of what I was seeing, and I'll get back to that story here in a minute. I did want to highlight here, I think Lola was hoping that I'd highlight some of the great stuff that WRF has been doing, and here's a little link to a little article that this intern who was working there at WRF wrote, and she got into the types of microplastics that were out there in cosmetics, and she's actually got a nice table in this piece that does an assessment of the various states in the U.S. and who's got legislation and who doesn't. But of course, Obama also banned the microbeads. The paper that you see there on the left is a white paper that I authored a year or so ago for Water Environment Reuse Foundation, which was an assessment of risk based on the current literature. And I've since done more lit reviews, and they really don't contradict any of the conclusions that are in that paper. And then they also came up with a nice fact sheet that you might want to download about microplastics that can help you talk to some of your colleagues and the public. So let's get down to the nitty-gritty here in the last 2 or 3 slides. The foundation of risk is that you've got to have exposure before you can have effects. And the fact that there is exposure does not equate to risk. Any of you that happen to consume a beer or a glass of wine this weekend are going to have an exposure, and it's going to result in elevated liver enzymes. And I would dare say that you wouldn't equate that with some adverse effect on your health. You have to have the dose to create the adverse effects. The lab studies that are in the literature, believe it or not, are having exposures that are hugely in excess of what is actually found in nature. The journal that I run will not publish a paper that uses environmental concentrations of any toxicant that are environmentally irrelevant. But that's what's been making it into the literature. And as Paracelsus said centuries ago, the dose makes the poison. Even water can be toxic. So it's not surprising that we're seeing adverse effects from microplastics because the organisms are being exposed at such high concentrations. So what are the right numbers? Well, if you look at the studies that have actually done a good job at monitoring concentrations, you'll see that the concentrations are around 32 particles per 1,000 liters at the worst places. A survey of wastewater treatment plant effluents in tributaries of the Great Lakes was finding a median of 1.9 particles per 1,000 liters. And now, if you were to look at the algae that was in that same amount of water, you would find tens to thousands of millions per liter. And let's take the Daphnia. The Daphnia is eating the algae. Do you think it could consume a microplastic particle with that kind of a ratio? Absolutely not. The chances are almost impossible. There are concentrations, having said that, in China that have been found in China in some of the areas where there's no treatment at all that are at concentrations that could cause an effect. But this is the only place that we've found these. So it's virtually impossible for microplastics to cause any adverse effect on zooplankton or fish larvae that would be the kinds of organisms that would consume these. Now, benthic organisms, that is, organisms that live in the sediment that are right below a wastewater outfall that was not operating well, possibly could be exposed to particle concentrations that might actually cause an effect. But that's really the only place that this could happen. There was a recent paper that's just come out in Environmental Toxin Chem that is a great review article, and the conclusions they find are similar to the ones that I have found and that Bart Coleman's in the Netherlands has found in 2 papers and that Kristen Connors found in 2017, and that basically fibers and fragments dominate, not microbeads. The in situ concentrations are more than an order of magnitude lower than what's required to cause an adverse effect. They cannot be a vector of ingestion of contaminated particles, contaminated chemicals, because the numbers are so low. And so the prey, the organisms that are being eaten by fish are the primary way that fish would get contaminated with PCBs or pesticides. It cannot be through the microplastics because they're just in too low a number. So we really need to have some realistic approaches. Fibers are what's really dominating, and that's primarily coming from polyester fibers that are being from your wash. That's what we find inside of fish and mussels, bivalves. But when we find them, the concentrations of the fibers are, again, very, very low. The wastewater treatment plants that are operating correctly are removing 90 to 99% of the microplastics. We need to really use some caution on these conclusions that we're seeing. This is a paper I thought you would be interested in that I just found recently. It was microplastics are found in human feces. Well, of course they're found in human feces, but does that mean they're a problem? That means they're going through the human and they're coming out the other end, and the concentrations are still low. Now, we certainly don't like that to hear they're in our feces, but it's not an adverse health risk. As I said, the depositional sediments below a wastewater outfall may be an issue. Polyester fibers, or if any microplastic is an issue, it's the fibers. But I don't think we're going to do away with polyester fiber clothing. What could be an issue are the particles that we're not even sampling that are smaller than 300 micron. A couple of studies from Korea have found the water, surface water, is loaded with paint, anti-fouling paint chips and fibers from boats. And of course, all marine boats are going to have anti-fouling paint on them to prevent the growth of organisms. And this paint is actually constructed to flake off. That's part of the anti-fouling ability. And these particles tend to be incredibly small and very hard to sample. So from my perspective, these actually could be an ecological issue, and we're just not really looking for it. So my last slide, we need to be focused on macroplastics, not microplastics. The stressors that we should be worrying about out there are things that you guys have known about throughout your career: BOD, TSS, nutrients, pathogens, and pesticides. We need to refocus the argument and focus on things that truly are causing adverse effects. The methods have to be improved, and they can't be these methods that no one can do because the equipment's not around. So we need to make some advances there. And we don't have any approved QA/QC for these counts. So we need to standardize the methods, and the government, OECD, and different organizations need to do that. We need improved exposure and fate models. And lastly, and most importantly, we need to do a better job of educating the public and the government about reality. Thank you very much.
Thank you very much, Dr. Burton. That was a really great overview. And so now we will move to our live polling. And so this requires everyone in the next minute and two to please answer the questions in the live polling. Why are you interested in today's webcast on microplastics? And at the end of the 2-minute mark, we'll give you preliminary results, and we'll showcase those results again once we hear from our other speakers. But we'd like to see what and why you logged on today, and so many of you. I can see everyone punching in their responses, so we'll give it another 30 seconds before we close the preliminary poll. Great. So from our preliminary poll, we have a great understanding of why you, okay, great. So just to summarize the poll real quickly, most of you are curious. That's very good. And 17%, so that was 54% of you are curious. 17% are concerned about possible new regulations. 16, a close 16 next to the 17, actively conducting research. You get a lot of inquiries. 6.5% of respondents said that, and 5% increase in other reasons not listed above. So if you could do us a favor in the Q&A section, tell us those other reasons that we didn't capture but brought you to the webcast today. We'll show you again at the end of the webcast and see if these numbers change. Thank you all for that participation. So now we travel next to Legoland. Our next speaker, Per-Henrik Nielsen, is a senior manager with VCS Denmark, and he serves as a focal point for development of optimization possibilities for VCS for Denmark. So we're really happy to have him and all our European participants today. So without further ado, Per-Henrik.
Thank you very much, Lola, and thank you very much for this opportunity to give you an insight on the Danish perspective on microplastic. VCS Denmark is situated in Scandinavia, in a small country called Denmark, up in Scandinavia. Shown on the map here, and some of you might not know where that is, but you're welcome to visit us one day and see a great little city there. We are one of the larger utilities in Denmark, situated in Odense, the city of Odense, the third largest city of Denmark, mostly renowned for being the birthplace of Hans Christian Andersen. We are responsible for drinking water supply to the city and wastewater handling as well. Next one. We are quite progressive on our wastewater treatment plant, and we've talked to quite a few of you possibly about our treatment plant. It's a medium-sized treatment plant that's treating effluent from around 400,000 people, but quite progressive on BNR with a TN, total nitrogen limit of around 4 milligram per liter and a total phosphorus limit on 0.25 milligram per liter. So quite progressive. We have optimized quite a lot, and without adding any carbon source, we have turned our treatment facility into an energy producing facility, and right now we are producing quite a lot more heat than we are using ourselves, and we are selling that to the district heating system, and even electricity. We are producing more electricity than what we're using. So we have a lot of things going, and of course we looked around and saw what was the next question, and for us right now we are looking on emission of N2O and methane. But another big question for us is what about microplastic? Why remove the microplastic, and what is it really dangerous? And Alan has just put that into perspective and probably indicated that it's not that dangerous in reality. But seen from a utility perspective, it's a field where we do have a responsibility, and we do have a lot of press on that topic. We are very frequently asked what is our view on this, and we do find that it's better to be active than being hit by regulation, and we are trying to put our fingerprint on the development in this field here. So in reality, how do we measure it? And that is not easy, and more interesting, can we actually remove it? It might not be equally popular, this slide, all over the world. Notwithstanding that in Europe and in Denmark, we take the sustainability goals from the UN very serious, and we do find that we both have a role and a responsibility to do better in this field here. And there's a number of these development goals where we can make an impact, and in relation to microplastics. So for us, it's important to see what impact we have on the environment, and can we do something about it. It might not be a big problem, but it's still a responsibility for us. And getting back to the more nitty-gritty about microplastics, sampling and sample preparation, that is really challenging. Our initial test, we tried to figure out how much microplastic do we have in the inlet and the outlet from the treatment plant, and just getting the sample size correct was a little bit of a challenge. We could sample 300 milliliters and get that through the filter in the inlet, and outlet 200 liters. So it's a little bit bigger than what you've seen in a lot of other sampling regimes around the world. We did have problems with fragmentation of material during sampling, and we were losing materials. It's very, very low amount of material that we have, and do we actually get all the plastic there? And contamination of samples, because people are using clothes when they are walking around in their lab. So it's quite tricky in reality. We looked at a number of different methods, and as Alan indicated, microscopes have been used widely. We have opted for more advanced methods, and the method that we have been using mostly is the Raman or FTIR have been used as well, and they are quite difficult to work with, and very time-consuming as well. We do find that the microscope potentially have a little bit of a problem, especially in the smaller particles, and it is a case of human error as well if you have a light microscope. So what's the result of our initial investigation? The initial investigation indicated very clearly that we were doing a fantastic job on removing 90 to 99% of all microplastics from the liquid stream. However, there's a really big need for a validation of the methods, because it is difficult to compare the methods, and different methods are giving different results and on different plastic types. So we know that we are removing a lot. We are not exactly clear how valid the methods are. We were hoping to make a cheap test, and we created an extremely expensive test. So it's not cheap at all, and it takes a lot of time. We were trying to evaluate the phase of plastic through the treatment process. We were trying to find out how much is getting in, where is it going, and how much is getting out. And we found that was quite difficult to get a precise picture of. During our investigation, we evaluated that microplastic in sewer overflow and rainwater would potentially be a bigger problem, especially if you're looking at the liquid or the recipient where the receiving the water. We are in all these methods having quite a big problem in seeing the rubber particles or carbon black, because the methods are all using or are normally using light, and carbon black is not very good at reflecting light. Everything indicates that a lot of the microplastic ends up in the biosolids. We did another case study, and we thought we better do something about this microplastic, and how can we show that we are doing something. So we looked at this sort of 2-in-1 solution where we could remove both carbon. That's very popular these days, to be able to redirect carbon for other usage and for methane production and in digestion systems. So that would be good if we could control that better. A combination of what's called an A stage and microfiltration for microplastic. And we even got as far as spiking some tests to see how much removal rate we could get. The results from the two plants we tested this on was very clear. We could see a rather large number of particles in the influence. We could see a substantially lower number of particles in the effluent, meaning that we would have a 99% reduction. The particle size were sort of quite small and varied a lot, really a lot, so it was difficult to determine anything. And we did see extreme big variations. We were looking for a number of different plastic types, and we covered what we thought would be the most predominant types. In the test we did, we added particles of a known quantity, and we could find them again using a UV light, and we could clearly see that we were getting up to extreme high removal rates. The conclusion from the case study is microplastic can be removed, or if not everything, at least a really high number of amount of plastic can be removed. At the same time, we could remove COD, and we would get a very good filter cake out of it. Still having some problems with capacity of the filters, of course. In summary, the sampling is difficult, and it's important. You need to get a decent amount of fluid in when you're sampling, and that is difficult because you get a lot of other things in when you're trying to find the microplastic. Measuring is very, very costly and not very precise. Well-operated wastewater treatment plants are removing microplastic from the water line, so it is probably coming somewhere else instead of, and it might be a good idea to look in the biosolids. CSOs would indicate, or some of the indications we're getting is that it might be a bigger problem, and we believe that there should be a bigger focus on tracing the source of the pollution here. That wraps up my perspective on microplastics here. Thank you very much.
Thank you very much, Per-Henrik. We now take it back to the state of California and have Shirley Walter talk to us a little bit on the wastewater and policy implication of microplastics.
Thank you, Lola. Hello, everyone. This is Shirley Walter. I'm going to talk to you about wastewater and current and future microplastics policy in California and nationally. We've seen popular press and some research suggest that severe ecological threat may exist from microplastics being discharged by wastewater treatment plants into aquatic habitats. But the reality is that microplastics are largely removed from wastewater before they're discharged. In light of the media attention on microplastics, Carr et al. 2016 conducted studies to help understand the removal of microplastics from the sanitation districts of Los Angeles County's treatment plants. When both subsurface and surface effluent were measured, they found one particle for every 250,000 gallons. The authors concluded that the particles found may have been due to airborne contamination. This means that the sanitation district's tertiary treatment facilities removed over 99.9999% of microplastic particles, and their full secondary plant, which discharges to the ocean, discharged one microplastic particle per 300 gallons, which was a removal efficiency of over 99.99%. Now, in contrast to this, Sutton et al. 2016 found that wastewater discharged into the San Francisco Bay contained considerable microplastic contamination. How much? The 8 San Francisco Bay wastewater treatment plants discharged an average of 0.33 particles per gallon and 7 million microplastic particles per day, which is a big difference. Although there have been many studies on microplastics in wastewater treatment plant effluent, there's no standard method for sampling, identification, and quantification of the microplastics, which complicates comparison of the results as well as future policy decisions. And the inaccuracies of the Sutton et al. 2016 study methods was documented in Diachenko et al. 2017. Primarily, it was that insufficient digestion was used for wastewater, which is high in organic content. And the particles are all often mistaken for microplastics, such as toilet paper, cellulose, hair, cotton, bacteria, and fat globules. So the takeaway from the Diachenko study is that visual ID only is insufficient, and you need a confirmatory technique such as FTIR. And you also need standardized sampling protocols. If you're calculating a wet wastewater treatment plant's average flow rates using a 2-hour sampling or a 24-hour composite, you'll get several orders of magnitude discrepancies in the count. It also depends on the time of day, the day of the week, the time of the year. So those should all be factored in. It's also been, studies have shown that there's no relationship between wastewater treatment plants' location and microplastics. Miller et al. 2017 concluded that there was no relationship between fiber abundance and wastewater treatment plant location or population density. And it showed that there were significant numbers of fibers upstream of the wastewater treatment plant, and that wastewater treatment plants were not the only source of pollution in the Hudson River. And the authors and other authors have concluded that potential sources, major sources, are atmospheric fallout. In 2014, the Norwegian Environment Agency conducted a study of microplastics sources and loadings, both in Norway and globally. The single most contributor was car tires. 5th was washing of textiles, and 6th was waste treatment. And the amounts are per year. What we conclude about sources from these and other studies is that the laundering of textiles and wastewater treatment plants are not a likely major contributor, and that aerial deposition is a likely major source. And on the horizon, biosolids as a pathway of microplastics in the environment and risk assessment will be a major focus. Recently, the EPA expert panel on microplastics put out a report, and in this graphic you can see a lot of different colors. You can think of it as a heat map where the warm colors are little information and low confidence, and the green is mostly good information, good confidence. And the takeaway from this is overall there's very little information known about the sources, transport, and fate of microplastics with low confidence in that information. And what little green you see is from marine trawls, which are usually 300 microns mesh size. And the microplastics found in wastewater are mostly less than 300 microns. So again, size does matter. So how does this all feed into what we're seeing with policy? Well, we've seen alarming warnings on the hazards of microplastics, which led to widespread banning and phasing out of microbeads. In California, we had the California Plastic Microbeads Nuisance Prevention Law. It was signed in 2015 and goes into effect in 2020, and it bans the use of microbeads in personal care products sold within the state. In December of that same year, the U.S. Congress followed suit and banned microbeads with the Microbead Free Waters Act. And in the federal law, it prohibits the manufacturing, packaging, and distribution of personal care products containing microbeads. And it bans in phases. The first phase bans manufacturing of microbeads in personal care products, and that began in July 2017. And the last phase will begin in July 2019, which will ban microbead-containing personal care products from being sold. Now, the exception to this act is that it's only for rinse-off cosmetics, like toothpaste or face wash. So this year, in 2018, the California legislature doubled down on the state's commitment to reducing plastic pollution and waste, and they sent several bills to the governor for signing, and most of them were signed on September 20th. So I'm going to go over a couple of those. One of the bills, SB 1335, prohibits non-recyclable and non-compostable takeout food packaging at state facilities, including parks, beaches, colleges, and fairgrounds. The straw ban movement, as well as other plastic waste-related policy, received a major bump in public consciousness in 2015, thanks to a graphic viral video by a marine biologist who extracted a plastic straw from the nostril of a live and very uncomfortable sea turtle. So AB 1884 is an example of public consciousness, which led to law in California, which requires restaurants to offer straws only upon request. This year in California also, the California Ocean Protection Council's, or OPC's, Ocean Litter Prevention Strategy came into effect. Now, the OPC has made understanding the impact of microplastics and microfibers in the marine environment a priority. And now, in the earlier iteration of this strategy, it was based on popular opinion, much like we've seen with early laws, but through a robust stakeholder process and pointing out some of the science that Alan pointed out, is now based on current knowledge of the status of the science, which is still in its infancy. The OPC will actually fund the development and validation of standardized methods for assessing microplastics in wastewater effluent, surface waters, stormwater, sediments, and in organismal tissues by 2021. They'll also convene expert scientists to develop a comprehensive research plan by 2024. And the goal is to better understand the pathways and sources of microplastics. They'll also develop risk assessment studies and determine whether reformulated textiles will reduce the loadings of microplastics to the environment. Now, if wastewater treatment plants are found to have impact on the environment, they'll research technological solutions in the wastewater treatment plants and in washing machines, including source control. The OPC, there's also a SB 1263, the statewide microplastics strategy, and it basically codified the microplastics portion of this strategy. And the OPC will make recommendations based on this to the state legislature within 5 years. SB 1422 is the California Safe Drinking Water Act, and it requires annual testing of drinking water for microplastics after a definition and standard method for testing is adopted by the State Water Board. And after that, testing will be required for 4 years. In addition to all of this stuff happening in the legislature in California, there have been additional efforts, including a Twitter campaign for plastic source reduction called #CaliforniaMustLead. There's also been the 6th International Marine Debris Conference, which was hosted in San Diego, California, which highlighted microplastics. And the Ocean Protection Council, as part of its focus on microplastics, is offering a grant to fund research on microplastics risk assessment and transport. That's due tomorrow. And the OPC has already funded a study of microplastics as a disease vector. And on the national scene, the Save Our Seas Act was signed this year, which reauthorizes NOAA's marine debris program through 2022, which continues research on marine debris cleanup and prevention. So looking forward, California can expect to see comprehensive microplastic legislation, including microfibers, in 2019. That was an update that was given by the OPC earlier this week during a strategy call. We can remember We should remember that effective microplastics policy should be based on sound science, not popular opinion. And to do this, we need standardized and validated methods that are needed to assist scientists and organizations to answer increasing public concerns associated with microplastics. We need to remember that you can't manage what you can't measure, and that, as Alan said, the QA/QC review of research is critical. We need to understand more about major pathways of microplastics, not just those that are well studied or easy to access, but those that include tires, boat paint, road paint, aerial deposition, agriculture, landscape applications, and more. And finally, microplastics risk assessment studies do not indicate that microplastics are a major problem, and we need additional high-quality studies to look more into this. Thank you. I leave you with a snapshot I took of an artist's rendering of Captain Charlie Moore. It's made from found trash on Stinson Beach, California. Captain Moore has been a pioneer for micro and macroplastics research and public outreach through its Algalita Foundation. This piece was shown at an art exhibit during the 6th Annual International Debris Conference earlier this year. And if you're interested, the artist is Tess Felix, and this is part of her Ocean Eco Heroes series. Thank you.
Thank you so much.
I'm going to turn it over now to Belinda Sturm.
Okay, thank you, Shelley. Good afternoon, everyone. It is such a pleasure to join this webinar, and I really just love the Water Research Foundation for bringing folks together from all over the world. My job today is to talk about the challenges and research needs for microplastic fate and transport. And as my co-presenters have stated, there are several areas that need work and that have research needs. And I'm seeing some of the questions come in as we're doing this, and I look forward to the Q&A. So I'm going to talk about 4 specific research needs. You've heard, I think, everyone mention that there is a real need for standard methods to identify microplastics. And, you know, we have the old adage that you can choose 2 of 3, faster, cheaper, better. And I feel like that is very true with the microplastic identification problem. But we do need to be able to measure these in wastewater matrices. We'd like for that measurement to be relatively quick, and we'd like for it to be accurate. I'll have some slides about each of these. The second thing I'll talk to you about is how the sludge structure and the properties affect microplastic fate. And we're really just starting to get into the research of this, and I'll show you some very preliminary results on that. Dr. Burton mentioned how microplastics are not likely to cause the transport of chemical or the degradation of chemical in a meaningful risk manner, but we do have some research about whether or not they can act as microbial carriers, and specifically thinking about DNA carriers into the environment, and that may have some ties to antibiotic resistance genes and emerging DNA contaminants, not just the chemicals. And then the last, and I've seen some questions come in about biosolids. Let me get to this. So we have done a literature review, much like Shelley and Alan and Per, and these are just some of the snapshots. And when we looked at this, we were also just thinking, how do we choose a filter size? So if we're going to go and try to collect wastewater, what mesh size are we going to target as a lower cutoff? And so there really isn't a standard that's been used in the literature. We also looked at different extraction techniques that have been utilized, and a variety of papers have used some combination of wet peroxidation, enzymatic treatments, density separation. What was clear is that there was quite a range of concentrations that were reported. So in the microplastic quantification, there are two types of analysis. There's visual counts, and this allows for quick processing times, high throughput, but has a real user bias that Alan mentioned. And then there are chemical analyses which allow for direct identification, chemical identification, and more confidence in those measurements. But these methods are time-consuming and expensive. And I believe these have been mentioned pretty extensively already. Within the visual detection, we can improve that over the simple visual identification by using Nile red staining. And several papers have done that, and we have compared that with the analytical chemistry methods. And I think that there will be more work to that, but those visual identifications will never be as good as using the chemical identification. Within analytical chemical identification, there is the FTIR, Raman, and then there are two others that are less clearly utilized. I have seen a question as to whether or not there are organizational efforts to establish a standard method. And I do know of colleagues across the United States that are working with an ASTM method, but I'm not at liberty to say anything about that not being on that project. So hopefully that work will come. Okay, so within our work, we did some initial sampling within Kansas, and this work was initially funded by the National Science Foundation and was led by high school teachers. So the 4 Kansas wastewater treatment plants that we initially worked with were also located near the high schools of our participating teachers. And this was some of our very initial data, and I'm going to use this data to highlight some of the impetus for biosolids research. So on the left you have the mass loading of the microplastics that we measured at the 4 wastewater treatment plants, and on the right you have the counts. Now these counts were not using FTIR, so these were dependent on visual sampling and were subject to that overestimation that has been mentioned. The key point for this, though, is that microplastics have been observed. I think anytime you're going to go out into the environment and look for a sample, you will find them. And then the question, of course, is that imperative from a risk perspective? We took those initial numbers and we took flow data from the Lawrence wastewater treatment plant, which I've worked with quite a bit, and we did just a range of simulations for the range of uncertainty of our data. And what you can see here is that the influent has a large loading, and then most of those plastics go to the biosolids, and then a portion of those, which would be green, would go to land application, and the smallest fraction of microplastics would end up in the effluent. And in our data, that showed that only 0.02 to 0.3% of the microplastics would go to the effluent, which sounds trivial for the scope of the problem. But when you look at that and you multiply that up, 16 plastic particles per liter multiplied by all of the wastewater in the United States in a day, that would give you 256 trillion plastic particles released from all of the wastewater in the United States per day. Now, I'm willing to say that maybe that number is high by 1,000 times based on the uncertainty of our methods. That would still be a very big number for plastics being that are released in the environment. Now, we've heard from everyone that gets diluted in the environment and perhaps doesn't cause an ecological risk, but that is why we're here today and we have so many people registered, as this is a big number for us to consider. Now, if only 0.3% of the microplastics entering a wastewater treatment plant are going to make it into the effluent, the remaining portion will end up in the sludge. And we have been working on what causes that capture of the microplastic within the sludge particle. In this experiment, we looked at lab-scale reactors, and we seeded the reactors with fluorescent microparticles. And you're seeing the fate of those microplastic particles with time of incubation. And what we've observed is those microbeads get captured within the sludge particle, that it is not a settling phenomena, it is more of a absorption and incorporation into the sludge particle itself. And some of our current research is focused on what controls that capture mechanism and whether or not we can improve the capture with an engineering design. These are some scanning electron microscope images in the bottom row and then light microscopy in the top row. And these show you a better image of the microbial colonization of the surface of a microparticle. And so this research is focused on whether or not the carrier material can act as a substrate for biofilm growth. So in this work, we took a sample of activated sludge and we extracted the suspended growth through sieving and then the microbeads through our extraction protocol, and then extracted the biofilm from the surface of the particle. And then we applied high throughput sequencing to look at the community composition in the activated sludge and on the biofilm on the microplastic carrier. And this is a snapshot of the complexity of the community, and I won't go into detail of this, but basically every spoke on this wheel is a different species, which we call an operational taxonomic unit, but that's relatively associated with species. And it just shows the wide diversity that's present in microbial community. So this slide by itself is not very interesting or groundbreaking, but the next slide gets us to a more interesting point. This is a Venn diagram from each of the 4 wastewater treatment plants. And I'll walk through this a little bit. So if we look at the Lawrence wastewater treatment plant, the upper left-hand corner, the blue circle is the number of operational taxonomic units or species that are observed in activated sludge. And the purple are the number of species that were observed on the microplastic biofilm. And then the overlap is the number of species that were in common. And then this is for each of the wastewater treatment plants we initially looked at. So what you can see here is that there was only about a 22% overlap in the community between the activated sludge and the biofilm. Now, we don't know right now if this is significant, if it has any ecological impact, but we do know that any biofilm that's released into the environment on the microplastic is somewhat unique from the community of the activated sludge. And I just said any biofilm that was released on the microplastic particle because coming back to our fate, our back of the envelope fate calculations, most of that release would be to the biosolids and not to the receiving water body. And so that leads us to the last question I will throw out and hopefully have more discussion with you is, what about the biosolids? So if we are land applying within the United States, and we've been pushing to land apply as a sustainability practice for decades, what happens to that microplastic load? And before we get to land application, what happens to the plastics through the stabilization processes, and particularly thermal processes? Because at ambient conditions, plastics are relatively stable, but when we use anaerobic digestion, thermal hydrolysis, or even some of the emerging technologies such as pyrolysis, what will happen to that microplastic through those processes? I am not aware of too much research being done on this. We are participating in some research through our National Science Foundation grant, and I know of at least one collaborator that's done preliminary work in this, but I think that this is largely unknown. And so my thoughts on this work so far is that activated sludge accumulates much of the plastic load to the plant. Less than 1% of that microplastic load goes to the water bodies, and the mass majority will be released through biosolids land application. The bacterial community on the microplastic surface can be transported into water bodies and into the biosolids application. And the impact that disinfection will have on that community, if you're in a country that practices disinfection, we have no data as to the ecological impact of that. So I'll just wrap up by acknowledging the National Science Foundation here in the United States and the Water Research Foundation and my lab group who does all of the work. All right, thank you.
Thank you, Belinda. And before we get quickly into the Q&A, I just wanted to mention these 3 resources, the fact sheet that Alan had mentioned in his slide. This was a collaboration prior to our integration, so it brings the drinking water, wastewater, aquatic, all into perspective. So it's a really nice compilation. Then Alan's white paper, which was focused on the aquatic system, so microplastic in the aquatic system risk assessment. And then this early science brief, like I said, we've been monitoring this topic for quite some bit now. This science brief was led by TZW out in Germany, Florian Stark and Stephanie Ring-Pfeiffer with GWRC led that. And the project that Belinda just described is ongoing, but this very last one here, method harmonization and round-robin comparison for microplastics, was a collaborative, again, led by TZW through GWRC, which is the Global Water Research Coalition. And we weren't part of the round robin or any utilities in the U.S. It was a lot of labs in Europe, but we contributed to that for the analysis, and that report is available. Okay. So with that quick resource and research activities and collaboration on microplastics, let's quickly go to our Q&A session. And we don't have that much time, but we have a lot of questions. So let's go quickly into it, and we'll start with our first speaker. And Alan, if you could take the question that was directed to you. It says here, as Dr. Burton explained, due to low microplastic concentrations in surface water, absorbed PBTs do not make a large contribution to the bioaccumulation of PBTs in aquatic life. based on that conclusion, it may not be necessary, but has there been any research into the ability of PBTs on microplastic, liability of PBTs on microplastics? That was a long question, but that came from MPCH Jess Matos, if that helps you find the question. So, Alan, could you respond to if there's been any research in the liability of PBTs? Thank you.
Yes, I have to turn the mute off for you to hear me. So there has been a bit of research on that, and just like most organics, it's driven by a lot of other factors, like sunlight, and is there air, is there not air around? But typically these nonpolar organics, highly nonpolar, will stick to the plastics for long periods of times, and that's why we find the high concentrations. But high concentrations are irrelevant if there's inadequate numbers.
So, Dr. Burton, could you also clarify how microplastics are not a risk to aquatic organisms' ecology? Is it because concentrations are too low, or the uptake by those organisms won't affect a significant population to have an effect?
It's the first, because most of the papers that have been published have shown an adverse effect when the concentrations are high, but that's the case with most any compound. So it's strictly a function of ecological risk is not there because the dose is too low. There's too many other things to eat. Orders of magnitude more algae to eat than the microplastics.
So I get asked this question a lot too, but this next question is also for you. They said they might have missed it, but why don't microplastics act as a vector for contaminants?
Well, I was addressing that on a couple of slides there, and it's strictly because the numbers are too low of the plastics. If you do a Google search for Albert Coleman's, Koelmans, he and I published a paper. He's in the Netherlands, and then he published a couple of other papers recently where he has modeled the data from lots and lots of different publications. And basically, the loading of organic chemicals is orders of magnitude higher from prey being the things that organisms eat, rather than the microplastic particles.
So one more question for you before we move to other presenters, and it comes from another speaker. And this is, how do you know that 30 to 70% of identified literature number for reported microplastics are false positives?
That was just the study that was done, did a comparison of different studies and actually measured false positives in those studies. So it was a very focused study that came up with those numbers. Suffice it to say, and you heard the other speakers say, there's a lot of error with trying to identify a particle as a microplastic particle. I would challenge any of you to do it. It's very, very difficult.
Thank you. So I'm trying to go as quickly as possible through all our wonderful questions. And this next one, the person says they've tried ramen, but it's really hard to get an analysis on microplastics that occur as fibers. Can you comment on how one might evaluate this form of microplastic? And Belinda and Per-Henrik, since you're doing active work, could you lead this one off?
So this is Belinda. Ramen is the method that we have the least experience with because we just simply don't have easy access to that in my lab. I know that other collaborators across the United States are preferring it, but I don't have any specific information to add to that question. Per?
Yeah, I mean, we haven't done our Raman work ourselves. That's been done by one of our cooperators. And we in Denmark have two different entities battling out whether FTIR or Raman is the best. We do see small differences between them, and they are all having problems. And I know that the company we were using for the testing had to make a rather large investment in new Raman equipment to actually get to get enough samples through, because it would take extremely long time for them to do it on a not optimized system.
And there's been some studies also that have shown in some areas most of the fibers are not polyester; they are actually natural fibers. They're cellulose or wool. So I don't know if that enters into that analytical issue.
I mean, with Raman and with FTIR, you do get a spectrum back from what kind of material you're pointing your light at. But it is correct that the fibers are really difficult, and we were having issues and difficulties with fibers, and because it's so much easier to find a micro bead from cosmetic than finding fibers in reality, because it's tangled up in everything.
Another issue with the FTIR is the pigments themselves on the microfibers or plastics can show up as a separate signal. And when you have something like a black pigment, it'll have multiple layers of pigments that are involved in making that black color, which can really alter the results.
Thank you. So, Shirley, if you could head the response to this one, because it has a regulatory angle. While it is great news that microbeads do not appear to be a problem, it seems like this is more luck than design. It seems problematic that personal care product manufacturers can add ingredients that will end up in a wastewater treatment effluent without regulation. What, if anything, should be done to change this?
Okay, so there's actually a loophole in the federal law for microbeads, and maybe closing up that loophole. If there's a concern about microbeads, which we've seen that's actually not an ecological concern at this point. But the loophole is that other products, such as some cleaning products and makeup that contains microbeads, is not included in the federal ban. So that's one area that could be tightened up. But again, these microbead bans were put into place before where there was a lot of research on risk assessment. And like Alan pointed out, the current research, very current, within the last couple months that's come out is showing that there's not a risk associated with the levels of microbeads that we're seeing right now.
Well, and that's a huge question that and the reality is, there's 15,000 or is it 150,000 new chemicals submitted per day for registration, and there is a pitiful amount of documentation at the federal level because they have a time. TSCA has a time limit on the amount of time that they can spend making the decision on a chemical. And they leave it largely up to industry to provide the information on the chemical. And so this is why we end up with a lot of chemicals on the market that are then later retracted from the market because they're not adequately assessed up front. Microbeads, I think, kind of falls into that. And my concern, as with most of the pesticides, is when you withdraw a pesticide and you replace it with something, it's been shown some of the replacements are worse than what was there to begin with. So I think most of industry is replacing the microbeads with silica, so a natural product. So maybe to those who are worried about microbeads, maybe they won't worry so much.
Thank you. We're going to take one more question for discussion, but I wanted to let everyone know that all of these questions are going to be compiled, and we'll get our speakers to address as much as possible, all of them, and shoot it out to, someone asked about an email group, but we would be in touch. We'll follow up with the folks on the webcast, with, especially answering some of those questions, if not all. So with that pressure off, in terms of addressing your questions, how about we spend the next 2 minutes and wrap up on this question here about removal efficiency. So the question is, both presentation reference high microplastic removal efficiencies in wastewater treatment plants. At what point in the treatment stream are microplastics removed? For example, might one expect similar microplastics removal in a secondary activated sludge plant?
I'll take that initially. This is Belinda. We have sampled across a wastewater treatment plant, and we see very clearly that most of the microplastics are incorporated into the activated sludge particle. And so that is not in the clarifier itself, but within the sludge particle. Part of the research avenue that needs to be addressed is what factors control that capture. And I think that is largely unknown right now. But I like the question.
So before we continue the discussion, please, all participants, remember to stay on and answer the survey questions at the end, which will be my last slide. So with that, is there anyone that wants to add to the conversation or dialogue on the removal efficiency on microplastics? Because there was a drinking water question about it too, you know, that they're not seeing anything there. So why is it even a discussion?
This is Tim Nelson. I would like to comment on the drinking water side. We are a little bit blessed in Denmark because it's only groundwater, and we were asked the question if we have any plastic problem in our drinking water, and we have confirmed that there are extremely little amounts of plastic in our drinking water. So if you have a well-functioning system, I believe that it is reasonable to expect that there will be very little microplastic in drinking water.
There were a number of studies that went straight to media instead of publication. They were not peer-reviewed, that were looking at bottled water and tap water and found microplastics in them. And I think that drove a lot of what we're seeing in California as far as microplastics in drinking water testing regulations. This is Shelley, by the way.
Thank you. So we're up on the hour, and I would like to thank you all. We had such great speakers, and our audience, fantastic, engaging audience. And I would encourage you all now to fill out their survey questions. Michelle, is there anything else we're missing? Could we show any maybe secondary results of the polling if the numbers changed?
I will send out the survey now. And I think that'll do it. Don't know that it's pushing out.
Okay, so there are 3 survey questions that we encourage you all to address about our webcast today. It really helps the foundation with future webcasts, improve suggestions for changes and what other topics you'd like. Let us know if you learned something new today and if you were able to apply what you learned to your work, and who else watched the webcast with you. And with that, thank you very much, and we look forward to having your participation on the next webcast, and a big round of virtual applause for our speakers today.